Alright, now that we've talked about the architecture of CUDA and how a CUDA kernel is basically developed, which essentially means that a CUDA kernel is nothing but just a simple function in C, and that function is called a kernel. And you will denote that function as a device function by using the keyword or the tag underscore underscore global underscore underscore before the definition of that function. Let's try to write a program, our first CUDA program. And this will be the start of our first programming lab, in which we would develop a very basic CUDA program before we get into studying and learning about parallel communication patterns. What we have, the program that I have in mind for us to develop by the end of this programming unit, is to write a program that takes a bunch of numbers and calculates their cubes. And we want to accelerate this with CUDA. I'll lay out the problem first, then we're going to go in CUDA and we're going to actually use and start up a sample program. And I'll show you how to start sample programs and compile them and see how they work. And then we're going to experiment a little bit with defining kernels and running kernels and things like that before we get into writing our cubes code. And then we'll basically modify our code to calculate the cubes of the number. The idea is to start writing a kernel. What we would do is we consider our kernel as a serialized code that works on one unit of data once, and it would be basically the code that we would run as one thread. Then in the GPU side code, we first declared our CPU in the CPU side code, we first declare our CPU pointers, then we populate the pointers with the data we have, we declare GPU pointers, then we copy the contents of our CPU pointers to the GPU pointers on the device, then we invoke the kernel and let them run on the GPU data, then we copy back the results of our calculations from GPU into the CPU, and when we're done, we free all the memory allocations that we calculated on the CPU and GPU. So almost any kind of program that you write is going to be composed of all these very basic steps. You declare your data pointers on your CPU side, on the host side, same with the GPU side. You populate your data pointers on the CPU side, copy the values to the GPU pointers, essentially transfer your data from host to device, have the device run the kernel on the device side data, and then copy the results back to the host, and then free up all the memory. Declaring the CPU pointers is actually straightforward. It's regular C. You can either use basic simple arrays for static memories, or rather for local memory patterns. If you just go with basic arrays, the problem is that you won't be able to use to dynamically allocate, which means that you will be bound to the size of the static allocations that you can have with your compiler. Or you can use pointers, which we will use pointers in this class, and you can either use alloc, malloc, or the new keywords in standard C or C++ to declare memory dynamically. Declaring GPU pointers is almost similar to declaring your host pointers or your CPU side pointers. Basically, you use regular pointer notations, and the only difference is that with declaring values on the CPU side, essentially you could basically do a malloc or an alloc or the new keyword to declare a pointer. So you do, for example, int pointer a equals new int 100, and so this is on the CPU side. Then you can declare 1000 integer values. On the GPU side, you'll use the function CUDA_malloc. And the CUDA_malloc takes two arguments. One is the size of the data that you want to allocate. So basically, if you wanted 1,000 integers, you need to basically allocate 1,000 times the size of an int, which is 4 bytes, and then the first argument is a void pointer to pointer, and then you pass to that pointer the reference of the device memory location that you declare. And the device memory is very straightforward. We declare them, for example, just like regular pointers. We declare, for example, int pointer device underscore something, and this will be my device pointer. So the device pointer here is going to be a pointer to a regular memory variable in C. To copy data between CPU and GPU, and if you have multiple GPU devices, you can copy between GPUs to GPUs. You can use CUDA memcopy, and the CUDA memcopy essentially takes as input, it's a function again, it's a CUDA C function. It takes as input a pointer, a device pointer, a host pointer, and the size of the data that you want to copy, and the direction. Now, the name of device and host pointer, these are basically your pointer variables. And so, for example, if you had like int pointer host something and device something, this guy will be the device pointer and this guy will be your host pointer. The size is the size of data you want to copy, and that essentially is the size of how many data points you have multiplied by the size of that data point type. And the direction is basically 3 directions you can copy from CPU to GPU, and its value is a constant called CUDA memcopy host to device. The host to device copies from host from your CPU to your GPU. If you write CUDA memcopy device to host, it copies from your device, from your GPU, into the contents of your CPU pointers. And if you wanted to go between device to device, if you wanted to communicate between 2 different GPUs, you'd use CUDA memcopy device to device, and that specifies the direction of your copying. So I'll stop at the anatomy of a kernel call. Because at this point I want to just go ahead and write a basic program and see how it works, how we can set our foundation and write a basic kernel, and then we get into calculating and calling these kernels. So now let's go into our programming environment and start writing up our shell of the program. Alright, so I opened up my Microsoft Visual Studio here, and what I'm going to do is I'm going to create a template CUDA project, and I'm going to go over this template CUDA project and talk about what each item is, and it does. And then since we want to write a program that takes as input cubes, or rather a big array, and calculates the cube of that array, we are going to delete all of the stuff that are as a part of this this project are created for us to run a sample CUDA code, and just keep the shell and the bare bone components that are required for us. The items that I talked about, declaring your host memory pointers, declaring your device memory pointers, and copying pointers back and forth. We're going to keep those, and then we're going to basically simplify our code. So to set up a CUDA sample program, we're going to go to File, New, and Project. And then under the projects, installed templates. You have a bunch of installed templates that you should already have, and you should also have the CUDA 5.5, or depending on whatever version framework you have, runtime version you have, you should be able to select the runtime template. we're going to give our project a name, and we're going to call it our first CUDA project. I usually uncheck the create new directory for solution. That way all of my files are going to be in the same folder. These are just my test sample files, and I really don't need that kind of directory organizational patterns with my projects anyway. And then press OK. And you will notice that your Visual Studio will set up your CUDA project automatically for you, and this simplifies a lot of the components that we would be interested in utilizing. So the first line of my code, or rather the first 3 lines of my code, are my preprocessor directives. The first line includes CUDA runtime, the header file, which contains all the functionalities that I would need to utilize for my program. The next line includes CUDA launch parameters. Again, another header file that gives me the ability to establish my parameters for writing my CUDA programs. And then it also includes stdio.h, which is a native C++ library, and its header files for standard input-output operations such as printf, fprintf, and so forth. This program is actually a very straightforward project, a simple project that is already set up for us. And there are 3 components to this process. The first line of C code that you have here starts at line 6, and this line is essentially your the prototype of a function that associates your pointer variables and makes a function call to a kernel, and we'll see the body of this function a little bit later. So the function is called add with CUDA, so that's the prototype of this function. The function that starts from line 8 to line 12 here, this is your kernel. And the kernel basically for this program that is automatically set up as a sample program for you in CUDA, it takes 2 input arrays and adds those input arrays element by element and copies the result of that addition of the elements into the array C. So for this project, the idea is that you have got 2 arrays, array A and array B. And so what we want to do is that we want to add these elements of these 2 arrays, element by element, array and A and B, and then the results to go into an array C. So basically you add each element of these 2 arrays, and then the result is going to be going to element C. So the kernel here performs that operation for me. It takes as input 2 constant integer pointers. These integer pointers are basically the beginning of array A and the beginning of array B, with the contents of the arrays A and B. And also you will have an integer pointer C. Then you add each element of array A sub I, to element B sub I, and the result goes to element C sub I. The main function performs like this. It starts with an array size of 5. You declare 2 variables, A and B, in terms of pointers, integer pointers, and automatically 5 values are going to be written. Then the array C is going to be declared with the array size, so you're going to have 5 integers for array C, and then you copy 0 to these arrays. Then the process calls the CUDA function, add with CUDA, which is your C++ function, and notice the add with CUDA, this is the prototype. It returns a CUDA error, takes array A, B, and C, and the size of those arrays, and performs the addition. We're going to get into the body of this function later. So array C, B, C, A, and B, and the array size. Then if the CUDA status is success, is not success, you print on the screen that add with CUDA failed, and the CUDA error may be not successful if you couldn't allocate memories, if you couldn't basically if you didn't have a CUDA device enabled or available. All these things would result in CUDA failure, and so you basically show the user that the CUDA did not succeed if in fact you turn an error from your device. Otherwise, you're going to basically show the result for C sub 0, C sub 1, C sub 2, C sub 3, and so forth. And then before you exit your program, you reset your CUDA device. If you were successful, you just exit the program. If not, you prompt the user that you were not successful. And the body of this program, the actual meat of the program here, starts with add with CUDA, which is again the function that I talked about, that your C++ Visual Studio compiler, or rather IDE, creates as a template for you. And so we are passing to this function add with CUDA 3 pointers, a pointer to C and pointers to A and B, and an integer, an unsigned integer, as the size. Now notice up here in my CPU code, lines 16, 17, and 18, and 19. These lines are those lines that I talked about declaring your pointers on the host side. Okay, and I said you can either use just directly the basic array declaration. Since size here was just 5, we could easily use a basic static array, just as we did here. If array size was 5,000, Visual Studio does not allow you to declare 5,000 items statically as an array, and you would have to use either the new keyword or malloc or alloc keywords, which are C keywords. These lines, these 4 lines here, are your host side declaration. Now let's take a look at device side declaration. I said that to declare variables or pointers on your device side, you basically do 2 things. One is you define or you declare those pointers, and as you see here, lines 45, 46, and 47 declare 3 pointers: dev underscore A, dev underscore B, and dev underscore C. These are my host side pointers that I'm declaring. Notice that these are not actually at this point, these are not created on the device side. These are basically merely I'm telling my compiler that I need these 3 pointers that I will be later declaring as device side. For me, for my own purposes, I put the dev prefix, or you can use just the letter D prefix to remind yourself that these pointers are to be the pointers that would be created on your GPU's GDDR, on your GPU's memory. And we'll do that with the CUDA malloc on line 58. So as you see, the CUDA malloc on line 58 for declaring, for example, the dev underscore C pointer here, it's going to create essentially allocate the dev underscore C that I declared up there on line 47, and it uses the size, the number size that I'm passing, which is 5 for this case, times the size of an integer, because dev C is an integer pointer. So if I wanted to declare 5 numbers there, 5 integers on my CPU, on my GPU, I need to declare 5 times the size of the integer, which is 4 bytes. So we'd use the CUDA malloc to declare C. Notice that if CUDA malloc, which is a CUDA function, it returns a CUDA status, and you can check the CUDA status. If it's not successful, you exit out. Basically, you go to the error, which is towards the end of this program, a label that then returns out of your function. We do the same thing for allocating device A pointer on CUDA. side on your GPU and device B pointer on the GPU side. So this process is very, very straightforward. To declare your variables, you basically declare an integer pointer or character pointer or float pointer or double pointer, however, whatever kind pointer you want. You define it just as a simple C function, and then when you need to allocate it at the runtime on your GPU, you invoke CUDA-malloc function, which basically takes two arguments: the pointer to the memory location you want to create and the number of memory units that you want to reserve for that pointer variable. So cumulatively, from line 45 to line 74, we define our variables on the GPU side, on the device side, and then we allocate those values. On line 58, 64, and 70, we declare the three arrays that we wanted on the GPU side. The next step, if you remember, was to copy your vectors from host to memory, or from CPU to GPU buffers. As I said, we use CUDA memcopy for this process. So we need to do 3 times of these CUDA memcopy. We take device A, pointer A on the host, the size that we want to copy, and then we copy from host to device. We do the same thing from pointer B on the host to pointer device B on the GPU. Size is equal to the number of array elements times the size of the array element, each of which is an integer here, and CUDA host to device. Notice for C, for the device C, I don't need to make any copies here from host to device, because on I have values for array A on the host and for array B on the host. Those are my input arrays. But C is my output array, is the result of my calculation. So all I need to do is to declare it, as you see on line 58 to 62. I declare its content, but I don't need to copy from host to device. It's actually the other way around. For array C, when I calculate my results, then on line 108, I memcopy from device to host, to the array host, the size times size of int, 5 integers, and this time I'm going to copy CUDA memcopy from device to host. So this is essentially the process, the end result of my process. And if I was successful, that's fine. If not, I'm going to basically write on the screen that CUDA memcopy failed, and then go to the error, which basically frees up my memory and returns out of my function. One of the things that I haven't talked about yet is once we're done with copying from host to device, and that is calling of my kernel, how to perform a function call on my kernels. We will get into this a little bit later, but for now, what I wanted to cover with this template project is declare CPU pointers, which we did in main, populate CPU pointers, which we did in the main, declare GPU pointers, which we did in our function, copy from CPU to GPU for A and B. I didn't go over the invoking of the kernel. Then I showed you where the GPU to CPU calculation works and how to free memory on CPU and GPU. So let's go over this one more time quickly. What I did is I declared my GPU pointers as, if you remember, I did an int A of array size, right? And same with B, and same with C. So these were the ones that I did on the host, on the CPU. Populating these pointers were when I actually wrote in the pointers values here. And we did these guys in the main function. Then for these guys, for declaring my GPU pointers, if you remember, I did an int pointer device underscore A, device underscore B, and so forth. And these I did in my own function, which which I called it add with CUDA, or your CUDA template adds with CUDA. For these guys, if you remember, we used the CUDA memcopy, and then we did from host to device. We didn't cover this part yet. We'll get to it later. And then for your copying of the result, we used the results C and dev C, and then we used device to host. So this we performed from device to host, and then finally we free up the memory. So this is the basic of writing of your very basic CUDA code. And what I'm going to do is I'm going to run this program, and then you'll see the result of this program and that how it works. And this is how the result works. The two inputs 1, 2, 3, 4, 5 for A, the array A, and then 10, 20, 30, 40, 50 for array B are passed to my kernel, and 11, 12, 33, 44, 55 is the result of adding each element to each other. So these guys on the right hand side of my equality sign are going to be the values for the C pointer. And so my program ran successfully, and it calculated the values, and it used CUDA to perform this. So next, what we're going to do is that I'm going to actually delete a lot of these unnecessary things, and I'm going to basically make this into a very basic bare bone shell that does not perform any kind of calculation, and then we will make this into just a hello world application, and we'll see how you can actually strip down this code to the very minimum that you can start out, and then how you can build on top of it. And then we're going to make this program into a program that will calculate the cubes of the input values. So now let's strip our program to get it to the very basic minimum that we need for calculating our cubes. And then we start out with a serial piece of code. We work on it and make it functional, and then we'll see how we can make that serial code into a parallel code with our kernel calculation. So first thing that I'm going to do is I don't need the array B in this case, because I'm going to actually use array A as my input, calculate the cubes of each element on it, and the result will go into array C. So I will not need my array B. So I'm going to take that piece out. Okay, now I want a function that calculates the cubes. I'm going to reform my add with CUDA function and just change its name to calculate cubes CUDA, and that will have an int pointer C, an input pointer for my input variable. I won't need the B, and I'll pass the size. So that would be my CUDA version. I'm going to also create a void function and call it calculate cubes CPU, and that would basically do the same thing. Take a C, a constant int pointer A, and an unsigned int for my size. So these would be my CUDA variables. Now for this, I will not also define my kernel yet, so I don't need my add with CUDA kernel. Remember that I changed the name of my add CUDA to calc cube CUDA, and it also only takes a C, A, and array size, and it returns. And then what I'm going to do is I'm going to also remove my printf function because it's going to look differently, and then CUDA reset device and CUDA and then return out of my function. Now, for now, I'm going to comment out my CUDA status calculation with the add with CUDA cubes, and I'm going to put multi-line comments here to comment that piece of code out. Our function also to be calc cubes CUDA. Let's call it calc cubes CUDA. Alright, it takes constant integer a pointer and an integer c pointer and declares the values. Okay, then we're going to take the device B as our calculation, and also device C, we take that out. Sorry, device B, we take that out because we don't need this piece of code anymore. We don't need the memcopy either. And I'm going to also comment out my kernel calculation. And since we don't have the device B and we didn't declare it, we don't need the reservation for it. Let me just compile my code and make sure that it compiles. Okay, it looks like my code compiles and it also runs. I did not do much of anything with this code. I did not create a kernel to call, and I just created a shell function called calc_cubes CUDA. It takes my host pointers. Then inside that function, I just do all my basic declarations. I also created a prototype for calc CPU cubes, or rather calc cubes CPU. Now in my main function, I have an array of size 5, an integer array, and I have an integer array C. So A is my input with 1, 2, 3, and 4 in it, and C is my output, which is essentially my array size. 5 elements in it, and all the 5 elements are 0. So how would I go about on the CPU side calculating my cubes? Okay, now to calculate the cubes, what I would need to do is, as you notice here in my code, I had an array called A, and it was made of 5 elements. I'm going to actually kind of make it like a large array here. And then what I need to do is basically to multiply this array 3 times each element by itself, and then calculate basically the cube of each element and write it into array C. So each element is going to be array raised to the number q, each element of the array. So array a sub 1 raised to the 3, a sub 2 raised to the 3, and so forth. If I had one CPU, one core, how would I write this code? What I would do is that I would take each element once, pass it to the CPU, calculate the cube, and copy the result out into the element. Then, so what I need to do is to have a counter. And since I have one CPU, one CPU will work on one of the elements. So the counter, every time I need to basically increment the counter. So every time I go in, I start looking at one element at the location of the counter, calculate the cubes, then increment the counter. So basically every time I'm done with one element, I basically go with one unit over. So the calculation of my kernel here is going to be, or my function here is going to be with a for loop implementation, starting from element number 0, going all the way to while you reach element number 63 or 5 or 7. In this case actually is 5, and then increment the counter 1 unit at a time. And then so the value for C will be the value at I would be equal to value of A multiplied by itself at location I 3 times. And this will give me my the results that I'm looking for. How about if I had 2 CPUs? If I had 2 CPUs, what I could do is actually I could start with element number 0 and then calculate each of the elements, each of the odd elements with CPU number 0, and then I could pass each of the even elements to CPU number 2. So if you had 2 cores, let's say CPU 0 and CPU 1, then you will be able to actually split this for loop into 2 for loops, and each of those for loops would run over half of the array. So for this case, I'd do element A or array A, and so array A will be a bunch of items, and same with array C, a bunch of items. So what I would do in this case is I'd basically go and give each of the even elements to CPU 0 and odd elements to CPU B to CPU 2. So I'd go with element 0 and pass it to CPU 0, calculate the cubes and copy it into element 0, and then go to skip element 1 and go and process element number 2, then skip element 3 and go and process element number 4, and so hop over and perform the calculations that way. Then for CPU number 1, or for core number 1, I would pass to it odd elements, calculate the results and copy them over, and then hop over 2 elements, 2 elements, 2 elements, basically, until you reach the end of your arrays. So in this case, what I could do actually is for my core 0, I could go for I equals 0, I less than the size I plus equal 2, and then calculate Ci equals A sub I multiplied by itself 3 times. Okay, and then for core number 1, what I would be able to do is to start with I equal 1, I less than the size, and then I equal plus 2. And my calculation would be essentially the same here as well. Take the input at each location, multiplied by itself 3 times, and you'd be done. If you had 4 cores, then you would basically pass the first element to core 1, the second element to core 2, the third element to core 3, the fourth element to core 5, and then you increment your items 4 at a time, and so forth. So in my case, and I'm giving you this overview to show you how I would start with the serial code, and then how I would split it into a GPU process. Now, if you look at this dual core, 2-core process that I wrote here, notice that each core works on half of my elements. Now, with my GPU, what I actually have is I can actually think of my project as running it over a bunch of GPU cores, each core getting one of the elements. So in in the case of writing my GPU core or my kernel core, what I'm going to do is I'm going to create a kernel. And my kernel will essentially will be just one line of code that takes one element and passes that element into its kernel on the GPU side. So each of these units will operate on one value, calculates the cube of it, and then multiply it. So with the GPU calculation, I will have many GPU cores, and that is the underlying theory here that we are going to be implementing. So let's start out with my serialized code with only one CPU that needs to run a for loop over my input array and calculates the cube of my input array. So this is going to be how it's going to look like. So my calculate cubes CPU takes the input value as a constant pointer a, the size that I'm going to calculate, and write into the element C and run it. So my void calc cubes CPU with an int pointer C, constant int pointer A, and unsigned int size. And remember, I have already the C pointer created and the A pointer created up here, so I don't need to do any kind of memory allocation on the CPU side. So all I need to do is to create a loop, and in my attempt I'm going to create a loop that starts from 0 and goes all the way to the size, increments each time it makes a calculation, and C sub I is going to be so calculate cubes of A sub I. Then in my main function, what I'm going to do is I'm going to call up the calc cubes CPU, pass my C pointer, my A pointer, and the array size, and then print on the screen A cube is equal to array size needs to be capitalized, and this should be my function. I take array A, initialize it at 1, 2, 3, 4, 5, array C, initialize all at 0, calculate the cubes on CPU, pass C, A, and array size. Calculation happens very simply. A for loop starts at element 0, goes all the way to the element size, which is 5 in my case, and increment it one at a time, and calculate the cubes of A sub I, multiply it by itself 3 times, write the results into C sub I, and then write out the contents and the process. So let's calculate this and see how it performs. And so as you see, A raised to the 3, A was 1, 2, 3, 4, 5, so each element 1 raised to the 3 is 1, 2 to the 3 is 8, 3 to the 3 is 27, 4 to the 3 is 64, and 5 to the 3 is 125. So my calculation actually runs, and it works reasonably fast, but I only have 5 elements. So this is my serialized code. Let me run this one more time. And so the process worked relatively quickly. Now, what if my array size is 500? I compiled it, and it took a little bit of time actually to perform this calculation, and it was noticeable on my machine. What if I make it 5,000? Now it ran, but it was a little bit slower on my CPU. So this is good and all. And what I did is I asked for 400,000 elements. And when I attempt to run this program, I get this problem. It just broke and it didn't compile. Why? The problem here is that when I attempted to statically allocate 400,000 ints in my array, my program, my Visual C++ compiler runs out of stack, and it will not be able to allocate that many static values. To solve this problem, I'm going to actually not run statically 400,000 elements, but rather I will allocate them from the heap, and I use the new keyword. So I'm going to reformat my constant integer a, and instead of creating it with arrays, I'm going to actually use a pointer and allocate that many integers. So I'm going to create an int pointer a, and then I'm going to make a equal new int array size. I'm going to also do the same thing. Create an int pointer c, make it new int array size. Now this should solve my problem by allocating in the compile time the numbers that I need, and we'll be able to allocate those values from the heap. What I need to do though, let's go ahead and write a function that will basically populate the array A. So what I'm going to do for array A is I'm going to populate it, and then I'm going to write in that the array A a bunch of numbers. And so what I'm going to do is I'm going to calculate the array location modulos 10 and write it into my function. So let's go and call it void initialize, and pass to my variable, my function, an int pointer a, and unsigned int size. So what does that function do? This function perhaps we'll call it initialize array. Initialize array int pointer a. And so for this function, I'm going to go for int I equals, actually also I need to unsigned int size for I equal 0, I less than size I plus plus, a sub I equals I modulus 10. So this should initialize my array. And then what I'm going to do here is call my initialize array on A and array size, and this should populate my array. Then I'm going to also create. I already created the C pointer, and then I'm going to calculate and perform this. So let's start this with like 4 values, actually 5 values, and let's see what happens. So 5 values from 0 to 4, the program works, and for 5,000 elements, the program still works. As you see, the results are still the same. For 50,000 elements, the program still works and performs the cubes and the operation. And for 500,000 elements, the program should still work. And of course, my program still worked for 50,000 elements. For 500,000 elements. How about for 5 million elements? Yes, the program still works for 5 million elements and performs the cube. Now let's take a look at the 400th element. As you notice, the 400th element is 0. How about 404? The last element of my array, 64. 407th. 343, 7 raised to the 3. Alright, so this is my serialized code, and it works reasonably and calculates my the cube of elements in the array A and puts them in the elements of array C. So how can we go about and write our program in CUDA and in parallel? It turns out that the process, as we covered so far in theory, should be fairly straightforward. All we need to do is to create a kernel function that takes as input the 2 arrays on the GPU side, on the device side, and then associate 1 unit per thread that is created and performs 1 unit of operation in that thread. There are multiple different ways to go about and associate threads of operations. And we're going to talk about how to associate these threads of operations in a little bit. But one way to do this is to create a block, thinking about the block as being one core that we talked about a few minutes ago, and having that core takes as input one element to perform the operations to the operation on. So my CUDA kernel starts with the keywords global, and it's a void function that calculates cubes. It's going to take as input an array and as output an array, and for each output element in the output array associates the cube of that corresponding input element from the input array. So I'm going to call this an out int pointer out, and I'm going to pass to it a constant int pointer because I don't want to accidentally change the value of my input array. So what would be the calculation here? Since this is my kernel that takes the input elements and cubes them and puts them in the output elements, I need to have an index for each of the elements. Now, I'm going to look at this program very simply and very straightforward. I'm going to think of each of the kernels belonging to one core, one operating core, which would have an index value. Now, if I create one block with one array, one thread in that block, my calculation, my GPU core is going to be essentially given a tag, a value, an input, an index, and I can use that index to peek into the input and output arrays. So I would give each of my kernels or each of my threads one index, and I use that index to associate with the inputs and outputs. How am I going to calculate this index? It actually is two processes, and I'm going to talk about it in a little bit. But the two processes that I'm going to use here is that I'm going to associate a block index that would have one thread. So each block would have one thread, and I use that as an index. So I create a variable called index, and I make it equal to block index.x. I'm going to cover this in a little bit, but here what I'm looking at, what I'm creating, is a one-dimensional block of GPU threads, each block with one thread. So that's how my kernel would look at the array. I'm going to run a bunch of blocks. Each of these blocks will have one thread, so each block will be responsible for processing one element. And then my output at the location index is going to be the cube, or rather the out at index is going to be the cube of in at location index. And that is all that there is to my kernel calculation. I'm going to dissect this kernel in a little bit, but let's see how we're going to be able to invoke this kernel. The good news is that in my CUDA calculate cubes CUDA, I pass the pointer A, and the array size. I'm going to allocate an int pointer on device for input and an int pointer on device for output. I call them dev A and dev C. I'm going to allocate them with the CUDA malloc, my device pointer C and my device pointer A, and then I'm going to copy the contents of A from host to the contents of device underscore A on the GPU. Then I'm going to invoke my kernel. And the invocation of the kernel basically is very straightforward. My kernel was called calccubes. So I'm going to call calccubes as the kernel. Then I'm going to pass to calccubes, as we talked about earlier, my parallelization parameters. How many blocks, and each block with how many threads. So in this case, let's run the size, which is the array size of elements. So I'm going to initiate and run as many blocks as there are elements in the array, and have each of those blocks to have one thread. And then I'm going to pass as the output device C and as the input device A arrays respectively. So I'm going to basically create 5, 10, 10,000, 400,000, 5 million, however many elements I have. I'm going to run that many blocks of CUDA threads, each of those blocks responsible for calculating one thread of operation, and each will take from the global memory device C and device A as output and input respectively, and then performs the calculations on these. So now let's run this process and see what happens. I compiled and it succeeded, and I ran. Well, this ran because I'm using the CPU version. So now let's comment out the CPU version, and now let's calculate the GPU version, which is calccubes CUDA. So I'm going to make CUDA status equal calccubes CUDA, C, A, and array size, and I'll see if I got any error. If not, then I'll reset the device, and that should give me my results. And so at the very end of this process, I print out the results. I just moved my printouts to the end of my program. So now let's compile, make sure that my program compiles. It did compile, and let's run it. Okay, my first problem is that I ran into the problem of an invalid CUDA launch, and that may be caused because of the huge number of blocks that I initiated. Let's make those blocks a little bit smaller so that they fit on my device. Great news! My program compiled and I got the correct results. Now, we haven't really talked about performance benchmarking and see how the performance works, but later on we will do that, and we'll see how we can actually compare the results on the CPU and the results on the GPU calculations. But at this point, because of the error that I got when I ran 5 million blocks, you notice that I got a CUDA error, and that was because I could not run 5 million blocks of operations at the same time on my GPU. In order for you to see how many blocks of operation you can run, and how many threads, and how many threads in a warp, and all that kind of information, you can consult your query device functions, which is a function in CUDA that tells you how many operations, how many devices you have, and what are the specifications of each of those devices and the operations on those devices. But apparently, the first huge number of blocks that I initiated was not really enough, or essentially my GPU could not handle that many blocks. Now, the good news is that the bad news was my GPU couldn't handle that many blocks. But the good news is that I initiated one block, so many blocks with one thread in each block. Now, what I could do is actually I could initiate a much smaller number of blocks, like 5,000, and associate within each block 1,000 thread, and that would basically create the large number of parallel processes that I needed to create with smaller number of threads and smaller number of blocks. And that would bring us to the next topic, and that is the mapping of our parallelization of the threads on our GPU units.